I don't feel so good.
Hello and welcome back to the Poisoncast, a podcast dedicated to explaining the deadly science behind toxins, venoms, and chemicals. My name is Scott Barnett. I happen to be a fourth-year PhD candidate in cell molecular pharmacology and physiology at the University of Nevada, Reno's School of Medicine. It's quite the mouthful there. On today's show, we're going to learn how it's possible to drown without a single drop of water in sight. So yes, it's time to drink the proverbial Kool-Aid on this episode of the Poisoncast as we discuss the lethal properties of cyanide. Not only has cyanide been the poison of choice for disgruntled spouses for decades, it has also been used by state governments to execute inmates, and it's been offered to astronauts, believe it or not. Russian astronauts, not American, but it's been offered to astronauts in the event that things go from really bad to even worse when they are very, very far from home. So it is a very widely used prolific poison for good or for worse. Now, last episode, I talked about the black mamba venom, right? This week, it's going to be cyanide. Now, while these are both incredibly lethal and toxic poisons, the way they kill you is significantly different, and that's what's really cool about them. Venoms, like the black mamba, these are biological molecules made by nature, and they're incredibly specific for what they target. The black mamba venom, as a matter of fact, it targets a single ion channel within your neuron, so just the tiniest bit of one part of one neuron, and it prevents it from relaxing, so you basically go into convulsions and you die. Venom is like a sniper's bullet that only targets, one really small part of, in this case, the neuron in your brain. In fact, it's so specific that even like the tiniest mutation in an ion channel that would renders the venom completely innocuous. If you ever wonder how like a honey badger, if you ever watch them on National Geographic and you see a honey badger get bit by a cobra or something, it kind of shakes it off and goes about its business of, killing the cobra and eating it. And that's because it was able to make a very small change to how it deals with that poison, and it's fine. Cyanide is a completely different beast here. Rather than being a big, complex biological molecule that's specific for that one ion channel in your body, cyanide only consists of two atoms, and it's really the chemical equivalent of a wrecking ball as it goes through your cell. Those atoms that we're talking about here, they're simply carbon and nitrogen. That's it. That's all cyanide is. By themselves, these atoms are not only crucial to life. As a matter of fact, like 3% of your body is nitrogen and 80% is carbon. So you have carbon and nitrogen all over you. But generally, carbon and nitrogen form into very stable, life-sustaining complexes. Cyanide is the exception, and we'll get into the chemistry about it a little bit more later on in the show. Most people, they don't actually realize that cyanide is naturally occurring, which is pretty cool. They're produced by certain bacteria, fungi, algae, all produce cyanide in different forms. They're actually a big component of the seeds of certain types of fruits. If you think of apricots or apples or peaches, they contain a lot of cyanide in them. In plants, cyanides they're usually bound to a sugar molecule in the form of what's called a cyanogenic glycoside. Not a big deal, but it's just a sugar and a cyanide bound together, and they defend the plant against herbivores. This makes sense because as a plant, you want to attract animals, because they will eat you and they will turn you into fertilizer, and it's all great for life. But if they go around chewing up and destroying your DNA that you're trying to pass along, which is the seed, what's the point then, right? Humans like to eat certain seeds too, and if you think of the cassava root, which we don't eat a lot of here in the United States, but in tropical climates, it's all the rage. And if you don't process the cassava root properly, it's been known over time to cause chronic long-term effects and kill people. It acts as a neurotoxin. So to back up one small step here, though, we were talking about apple seeds having cyanide in them. There's a lot of lore out there about apple seeds being able to kill you, and they act as cure-alls for all types of stuff. I did a little bit of back of the envelope math here, the cocktail napkin math, and what I've determined was that you need about 100 grams of apple seeds to kill an average adult based on the cyanide content in there. One apple seed weighs about 0.7 grams. That means that you have about 143 apple seeds, considering each normally store-bought apple has about 10 seeds. Ergo, you need about 10 apples to kill you. Or you would need about 1 apple for like a 12-pound dog or cat, and a horse would need about 100 apples. Now, that's not that much at all, but it's not nearly as deadly as you would think. First of all, these seeds have a very tough coating to them. It's a natural protectant from the cyanide inside. So you would have to grind those up into like a very fine powder and then feed them all in one dose. Your body's pretty good at removing small amounts of cyanide over time, so this is very unlikely to happen, but in theory, it could. So, now, while the dangers of eating these seeds have been known for centuries, hydrogen cyanide, it wasn't isolated at all from a pure form until 1786, and this gentleman named Carl Wilhelm Scheele extracted it from a purified Prussian blue dye. And unfortunately for Dr. Scheele, its toxicity was figured out pretty quickly when he broke one of his flasks containing the hydrogen cyanide that he had extracted, and well, that was the end of Mr. Scheele. So sorry to hear. But despite the auspicious discovery of cyanide by Dr. Scheele, cyanide these days is used all over the place as an industrial chemical. It's actually very valuable, and we make thousands of tons of it every year. It's used in metal extraction and refining. As a matter of fact, here in Nevada, we have a lot of silver and gold refineries here, and they use it all over the place for that. It's used for electroplating. It's used for photography in some instances. It's also used for fumigation. So this is all over the place here. And besides the industrial use, though, and this is a very interesting aspect of cyanide, it's been very popular for suicides, probably because it's quick and relatively painless, judicial executions, and, of course, murder, which we'll talk about. Okay, so hydrogen cyanide as a gas, as I said, has been used for these judicial executions in some states of the United States where cyanide is generated by, you take a potassium cyanide pellet, which is not too dangerous by itself. You drop it into some sulfuric acid beneath the unfortunate person who's going to be executed, and it forms cyanide gas here. The state of California executed a man named Carl Chessman in this manner, and this was in the early 80s, and I remember this as a child. It actually stuck in my brain. People were holding up signs that said, "Plop, plop, fizz, fizz, oh, what a relief it is." And if you remember what that's for Alka-Seltzer, which is an effervescent tablet that, makes you feel better, and they were using it to say that this is how, the same basic principle. You're dropping the tablet in the sulfuric acid, and you're going to kill the guy. So that was a very macabre way to do this. I don't think that would fly these days, to be honest with you. People are as a society moving away from the use of the death chamber, and it was very celebrated back in the day. So I'm sure this was a very bad man. I'm not saying he didn't deserve to die or not, but we just don't do that so much anymore. All right, enough about the death chamber here. I will say, though, that in the U.S., we've actually executed about 24 people via the gas chamber, and the last one was in 2010. We basically stopped doing it. Part of it was because people couldn't get the chemicals they wanted, which seems odd to me because they're all highly available. But I think we just don't have a taste for it anymore. Although I just saw on the news that we actually have a gas chamber here in Nevada, and money's been allocated to fix it up so that it's, I guess, all painted and spiffy, but whatever the case may be, so maybe we'll end up using it here. So I should note that while I find the science of poisons to be fascinating, I feel like I need to say this a lot, I find their actual use to be repugnant and horrifying. Most gas chambers, especially with the gas chamber, it takes 8 to 11 minutes to kill someone, or before they even lose consciousness, and it takes longer to kill them. It doesn't seem like a very humane way if we're going to kill someone. But beyond that, it's just these are really nasty things, and please don't take this as some sort of endorsement of me. I find the biochemistry and molecular biology fascinating, and beyond that, I'm hands off here. So, moving on. Cyanide. Okay, in the pure form, it's called Prussian Acid, and this is a historical name for it, but you'll still see it on some containers. And it was a very popular suicide agent of the Third Reich, so we're going to talk about suicide here. It was used by Erwin Rommel, the Desert Fox, if you remember. He was actually a brilliant general, and he was accused of conspiring with that plot, if you remember, to kill Hitler. A bunch of high-ranking people said he'd pretty much lost his mind, and we're kind of batting for the wrong team. Well, they found out, and they forced him to take a cyanide pill to kill himself. Adolf Hitler's wife, Eva Braun, also killed herself in this way, as well as Hitler's number 2, Heinrich Himmler, if you're a fan of history there. So the Germans had a very strong love for this gas, I guess, because they also, in the form of if you've heard of a chemical called Zyklon B, which is very ominous and scary sounding, for obvious reasons, it was used by the Germans in extermination camps during World War II, and millions of people lost their life to this poison. So it's a pretty nasty thing. That's the bottom line. It's just an awful chemical here. But probably most famously, and if you're old enough to remember this, I think this was just before my time yet, it was in 1978. It was Jonestown. If you guys ever heard of the Jonestown group in here, this is in Guyana, where there was a mass suicide by people. Over 900 of their members of the group called the People's Temple were either forced to drink or this flavor aid, like this Kool-Aid, basically. That's what you call drinking the Kool-Aid. If you've ever heard of that before, it's because these people in Jonestown were forced to drink cyanide in this Kool-Aid type mixture here. And I guess people were like, if they said no, they just like ran up and jabbed them with a syringe full of it. Yeah, pretty good times here, right? So there's that. And many people wrongly think that, if you remember the Heaven's Gate mass suicide in 1997, they're the people that wore the sneakers, and there was the comet Hale-Bopp, and they thought that in order to take their ship to the aliens on the comet to go off to another place, they had to kill themselves to do it. They did not use cyanide, so hey, there's a tick in the positive marks there. The members of that group took a phenobarbital mixture mixed with applesauce and vodka, which, to me, all things being equal, I would imagine would be a much more pleasant way to go, because you would basically feel high and then you would go to sleep. So one last fun fact here. Hydrogen cyanide, it was used as a killing agent for many years, and it may still be, for all I know, to kill whales in the harpoons. They dip the tip of the harpoon in a hydrogen cyanide mixture, and it kills the whale fairly quickly here. So let's learn how cyanide kills you. Now that you know that it's very popular, what is it actually doing here? Now, there are two ways that cyanide can get to you. One's an acute dose, and that means you just get a whole bunch at one time, and the other is kind of a chronic long-term exposure, which I guess I'll call the disgruntled spouse method. A little in your coffee each morning. The acute dose, though, is real interesting here. So the LD50 for ingestion of hydrogen cyanide is 50 to 200 milligrams, or 1 to 3 milligrams per kilogram of body weight. This calculates out to be about the size of an ibuprofen for your average size adult. If you did not listen to the last podcast, a very brief explanation of LD50, which is really important to understanding all poisons. It stands for lethal dose 50%. And that's a fancy way of saying that if you took 100 mice or 100 people or 100 of any organism based on body weight, if you gave a certain dose, 50% of them would die, 50% would live. And it's a general way of determining how much poison it would take to kill an average person here. So LD50 for hydrogen cyanide is about the size of an ibuprofen, which would be convenient if you wanted a suicide pill, and it's easy to hide, and it kills you within 1 to 2 minutes. So that's probably why one of the reasons it's so popular. When it gets into your system, unlike large molecules, cyanide is so small that whether you inhale it or you ingest it, within seconds, it will enter your bloodstream. It doesn't take long at all. If you have a really big molecule and you ingest it, it can take hours for it to get through your stomach, to get into your intestine, to slowly work your way into your bloodstream, and these can take a very long time for it to affect. But really small molecules, they just wiggle their way between everything, and they can get in your blood, no problem. So we go from bad to worse, though, because it turns out that hydrogen cyanide, not only does it get into your blood system very quickly, or your blood very quickly, it has a very high affinity for ferric iron, which is part of your hemoglobin in your red blood cells. And it binds there and it prevents oxygen transport. That's really bad. And if this was all it did, that wouldn't be stellar, but cyanide's primary role is way more insidious. And in order for me to explain what it's doing, you just get a little bit of a science lesson here. And if you're listening to this, you probably don't mind so much for the science lesson here. I'll keep it simple, though. We'll go freshman in high school level here. We all know that oxygen's really important if you enjoy living. That's pretty obvious. Now, have you ever wondered why you actually need oxygen? Why can't we use nitrogen or helium or something else, another gas instead of oxygen? Why is oxygen so critical to our survival? Well, the answer comes down to electrons, as it does for really any chemical reaction. Each and every type of molecule in your body has a different number of electrons floating around its core. We've all seen the drawings and the animations of electrons going around. Great. In fact, the funny thing is they don't fly around random like at all. They are, in reality, they're organized into different shells of electrons around that center core. Think of a gobstopper. It's got these different layers. Now, technically, they're not real shells. They're differing. The electrons have different energy states, and that will change the probability of being at different levels in the molecule. But don't worry about that right here. What determines, though, how oxygen or helium or nitrogen or whatever atom you're thinking about, what determines how it's going to react is that outermost shell of electrons, which is called the valence shell. So you've got all these different layers of electrons on the atom, but it's that outermost one that is really critical to how it's going to behave. And it turns out that the outer shell of electrons in oxygen, they are arranged in a very precise way so that it likes to share and borrow some electrons, but not too many, and it's got very unique chemical properties in this sense. As a matter of fact, on a side note here, if you look at the periodic table as far as sharing electrons, and you go all the way to the right-hand side of that table, which has all the little symbols for the different atoms on there, that very last column on the right-hand side contains elements that are real prudes when it comes to sharing their electrons. They don't want to give any of them away. They're very happy with how they are, and they don't react with anything. You can take helium or xenon or argon or any of those fun-sounding ones. You can mix them with anything. You can do whatever you want. They're just not going to react, and these are called noble gases for that reason, because they're very noble and they don't want to react, and they're very calm. So, fun side fact there. So back to oxygen, right? Why do we need oxygen? When it enters your cell, any cell for this fact, because almost all of them need oxygen, the oxygen finds its way to the mitochondria. Now, remember from high school, the mitochondria is really the energy factor of the cell that makes ATP. That's what its goal is, and it needs a lot of oxygen to do this. Like I said, the mitochondria's most important job is to make this ATP, which is a very fancy way of saying that the mitochondria is like making gasoline for the entire cell. And in order to do this, it takes oxygen. Remember that oxygen has, on that outer shell, has a couple of electrons that like to interact with things. It takes that oxygen and it steals a couple of the electrons from it, and it uses that energy to make ATP. As a matter of fact, the oxygen with hydrogen turns into water, and those extra electrons turn into ATP, which is our gasoline for the cell. And when you have enough ATP in your cells, you feel good, you've got plenty of energy. When you don't, you start to feel exhausted, and your body, and the way your body deals with not having enough ATP is that it starts telling your brain to take deeper breaths to get more oxygen, so it can start getting more of that awesome, tasty oxygen, so it can make more of the ATP. When I started this episode, I had mentioned that cyanide was the equivalent of drowning without water. And that could not be more accurate. When you hold your breath and you dive to the bottom of a swimming pool, that feeling you have, that desperate need to take in air, is just your cells sending a message to your brain saying that more oxygen needs to be taken in because I don't have enough ATP right now. With cyanide, the exact same signal is sent to your brain, except it doesn't matter how much oxygen you have, because the cyanide is blocking the door to that ATP making machinery within the mitochondria here. So you are really drowning without water. You can have all the oxygen you want, but your cells are not able to breathe, they're not able to respirate, and you essentially die from a lack of oxygen. What does this actually feel like? Unfortunately, the signs of cyanide toxicity, if I can get it out, at concentrations that lead to death, these are very well described within the literature. Anything greater than about 2,000 parts per million, and once you ingest that, once you inhale it, you get this brief sensation of dryness in the mouth, burning on the throat, which hydrogen cyanide is a mild acid, so that's probably that initial burning. It's because it's an acid. And you get a suffusing warmth throughout the body, which sounds quite pleasant by itself, that is. And you get a hunger for air, which is very what you'd expect. You're one of the first things you do is called hypernia, which is deep breathing, taking deep breaths in. And sometimes this is so depressing. It says sometimes this is followed by a brief outcry following the first breath, which is probably your body getting this weird shock, like something's not right here. And if the dose is high enough, you tend to lose consciousness in well under a minute. And that's probably again why this is such a popular poison within the suicide community, because it's fairly painless and you die with under a minute here. And the effects on the body are really systemic. It can affect your vascularity, your pulmonary system, so your blood and your breathing. Your central nervous system gets attacked quite quickly because it needs a lot of oxygen. Your heart gets affected quite quickly. Your visual, your autonomic system, which is your fight or flight, endocrine, metabolic, everything is affected quite quickly here. There is one of the main reasons we know about a lot of this is there was a chronic exposure to factory and mining workers, and back in 1975 these 36 male electroplating workers in Egypt, they were exposed to a whole bunch of copper cyanide and sodium cyanide and all these other forms of cyanide, and they ended up having really severe neurological, respiratory, cardiovascular effects. And these symptoms, unfortunately, will last months, if not even years, if you get this chronic exposure. So it's not good there. And it gets even worse if you've got this long-term exposure. You can get pancreatic diabetes. You can get vitamin B12 deficiencies. You can't uptake iodine as well, so you tend to have thyroid issues. You can get goiters. It's all really bad, so not something you want here. But the good news is there is an antidote if you get enough of it to hurt you, but not enough to kill you instantly. And generally what they use is amyl nitrate. And it acts as an oxidant, and it causes the formation of something called methemoglobin, which is a fancy way of saying that the cyanide will bind to this other type of hemoglobin in your body so that your normal hemoglobin can continue to transport and use oxygen, and it's a way to get it out of your system here. On a side note, amyl nitrate is a popular party drug. It causes a brief euphoric state, and it's often combined with, we'll say, cocaine and ecstasy, all that kind of fun stuff here. So at least as you're being healed, you feel good. Not only are you not going to die from the cyanide if all things go well, but you get a high out of it too. So I guess, if we're going to put a silver lining on this cloud, that's probably it here. And the availability of the antidotes, they varies around the world, but this is typically you can get something if you're going to work near cyanide here. So, well, that's going to end it for Tier 1. Tier 1 is our nice intro to it, some brief chemistry and science behind it. But now we're going to dive into Tier 2. If you don't care about the hardcore biochemistry and the science of this, we thank you for listening, and please tune into the next show. If you are a science geek and you enjoy some hardcore science, strap in, because we are going to go into Tier 2 right now. Some basic chemistry for our cyanide chemical here. Part of the reason it's so energetic and it's able to react is that it forms a triple bond between carbon and nitrogen. That's really the defining characteristic here. And if you have a triple bond between nitrogen and carbon, nitrogen in its natural state based on its valence enjoys 3 bonds, so it's happy there, but carbon enjoys 4 bonds, and so we have a difference here that is going to cause it to be reactive. Furthermore, cyanide has a tautomer, which goes from HCN to HNC. And if you remember, I actually had to look this up because I am not an organic chemist, but a tautomer, it's a reaction that it causes the formation, it causes a migration of the hydrogen atom. So you're basically just shifting its position. Rather than being HCN, it's HNC. So good times. Now you can remember what a tautomer is as well. It is highly miscible in water, which means you can dissolve it in water quite easily. And it is only a weak acid. Its pKa is 9.3. And if you remember, like the higher the number, the higher the pKa, the lower the acid is. So, I mean, if you think of acetic acid, which is, vinegar, it has a pKa of 4.75. So it's quite a bit less acidic than even an acetic acid here. Hydrogen chloride, on the other hand, which is like the strongest acid out there, is one of them is -7. So big range here, and it's not that acidic. Okay, boiling point. Let's do this here. So it's a gas at ambient temperatures, but it very easily boils at 25.6 C, which is 78 degrees Fahrenheit. So that will boil off quite easily and become very toxic as it enters the air here. It has, as a salt, it's called a hydrocyanic acid, and there are tons of salts out there. It's used in tons of different forms, like potassium cyanide, sodium cyanide, cupric cyanide, hydrogen cyanide, which is the one we generally deal with here, because it's going to dissociate most with the hydrogen. It tends to. With all these different salts, you'll have different pKa's and a different affinity for water and likely to break down, and hydrogen cyanide is the most deadly of them here. So many of these cyanides, though, are highly toxic, and the cyanide anion, it is an inhibitor of, so we'll go into more detail about what is actually inhibiting here. It's inhibiting the enzyme cytochrome C oxidase in the cell, and it's the fourth complex of the electron transport chain, which is found in the inner mitochondrial membrane, if you remember, in eukaryotic cells. The electron transport chain, it's also known as cellular respiration, if you remember that from high school or college. This is ultimately how ATP is generated, and without it, as evidenced by the cyanide, sticking a wrench in the gears of this process, you will die very quickly. There are a million videos on YouTube and websites if you want this explained to you in great depth out there, but the basic premise is that in the inner mitochondrial membrane, there are four complexes that shuttle electrons around. It begins with NADH reductase, it moves over to cytochrome C reductase, and then it finally goes to cytochrome oxidase, and finally, of course, you go to ATP synthesis from there, but it's the cytochrome oxidase that is interacting with the cyanide. Cytochrome oxidase is also called complex 4, and what it's doing is it transports 2 electrons from cytochrome C to the mitochondrial matrix. At the same time, 2 hydrogen ions are pumped into the inner mitochondrial membrane space, and oxygen is reduced to make water. And this is really at the larger level why we need oxygen to survive here. The O2 and the hydrogen form a complex, and then the oxygen is reduced, and you get water, and then that is used to, energy is used to make ATP here. If you remember your basic chemistry, Leo goes Gur, lose electrons, oxidize, gain electrons, reduce. So that oxygen is gaining electrons here as it is being reduced. So the binding of cyanide to the enzyme prevents the cytochrome oxidase C, prevents the transport of electrons from the cytochrome C to the oxygen. As a result, the electron chain is disrupted, and this means that the cell is no longer aerobically able to produce ATP for energy. Tissues that depend highly on aerobic respiration, such as the central nervous system and the heart, are particularly affected by this. This is an example of what we call histotoxic hypoxia, which is drowning at the cellular level. A side note about ATP, just go there for 1 second here. So we talked about how the electron transport chain ultimately makes ATP, and cyanide prevents this. If you ever wondered why, what rigor mortis, like why does that actually occur? Rigor mortis is Latin for stiffness from death. And in order for your muscles to relax, the myosin in your muscle has to bind ATP, and if you do not have ATP around, your muscles are in this locked state. If you are forming a muscle, you're actually have an ADP form, or an ADP bound to the myosin, and it forms that locked state between the myosin and the actin. When you do not have ATP around, that just remains in this locked state. So when your muscles are relaxed, it's because there's plenty of ATP around. And if you get like a cramp from exercising real bad, your muscles locking up, it's because you don't have enough ATP, because you weren't able to utilize oxygen and energy and all that fun stuff to make it. So that's it. So back to the poisoning here. So when you take this in, and this is all happening to you, you get an increase in blood glucose, an increase in pyruvic acid via the citric acid cycle. You get lactic acid increase. You get NADPH levels increase, and you get a decrease in this ATP to ADP ratio, which is why you're going to start cramping up here. What next here? So, I like this part. I'm a pharmacologist by training, or I'm being trained to become a pharmacologist. That's probably the best way to say it. And I really like inhibitors here. Cyanide is a non-competitive inhibitor for this cytochrome C oxidase. Specifically, the cyanide ion binds to the iron and the heme subgroups of the cytochromes, and that's what's interrupting this electron chain. Now, if you remember, non-competitive inhibition is a type where the enzyme inhibition, where the inhibitor reduces the activity of the enzyme and binds equally well to the enzyme, whether or not it has a substrate bound to it. So the two components to an enzyme working is you have the enzyme itself, you have a substrate that needs to be worked on, and the substrate binds to the enzyme converts that substrate into probably a couple different things, and then you're done here. So cyanide works whether or not a substrate's bound there or not. The other type of inhibitors are like competitive inhibitors, so that actually prevents the enzyme or the substrate from binding to the enzyme. It fills that little gap where the enzyme where the substrate will go to, and so it just can't work on it. The other type is uncompetitive inhibition, where the substrate binds to the enzyme, then the inhibitor comes in and it prevents the enzyme from working on the substrate because the inhibitor is bound there. So you have competitive, uncompetitive, non-competitive. But most of us remember that if we've been in biology class. Okay, hydrogen cyanide. Lethal concentration is about 300 mg per meter squared, and with this it will kill a human in about 10 to 60 minutes here. Anything more than about 3,500 parts per million is going to kill you very, very quickly here. If you remember, there was a terrorist group in Japan, I'm trying to remember the name of them. They had a big plan to release hydrogen cyanide into the subway system a while back, and they decided not to do it because of this very fact here, that under, even if you have a whole bunch of it, there's a tons of volume in the subway, and the concentrations were not going to get high enough to be highly lethal. They'd probably kill some people, and it would cause a lot of scare, but they wanted to kill a lot of people, and so this wasn't a good way to do it, they ultimately decided. So I guess that's another positive. So let's talk about the antidote here for just 1 second, and we'll close this out here. There are two primary things they use in the antidote, which is methylene blue and amyl nitrate here. What both of these do is they increase the amount of methemoglobin in your blood plasma. Normally you have trace amounts of methemoglobin, but this increases it a whole bunch. And best way to describe methemoglobin is that it has a heme group with an oxidative state of 3+, which is the ferric state of iron versus the normal ferrous state of iron in your normal hemoglobin, which is a 2+ oxidative state. And what this does is that the cyanide will preferentially bind to the methemoglobin, which does not carry oxygen. So it's kind of distracting the cyanide away from the normal hemoglobin, which does need to carry the oxygen to the cells, and it binds it up and it makes it unavailable for use here. So just by sheer, it's kind of a vacuum cleaner going around sucking up the cyanide so that the normal hemoglobin can do its job here. And you're just lowering the global concentrations of cyanide in your system, and hopefully you can recover from it. And that's really the only thing the antidotes can do here. And that's it. So maybe you'll live, maybe you won't here. So let's wrap it up really quick. Cyanide is very scary. I think we've concluded that quite nicely here. Hopefully I made a good argument for that here. It's also extremely fascinating from a biochemical standpoint here. I mean, being such an active reactive chemical that will go in and it will form a complex just with cytochrome oxidase C and bring down the entire system is a pretty cool thing here. I think probably the reason it's been so popular, it's been in the media, is that, you know, it's kind of scary that it can be readily purified from ingredients you can get just at the grocery store, you know, from apple seeds or apricot seeds. And that alone is not very cool, and it probably is a good reason to be concerned if you're around someone you don't trust, I suppose. But ultimately, it does a lot of good too, because it's used in a lot of industrial applications that, if you got a gold ring on your finger, it's probably touched cyanide at some point. I don't think I have anything else to say. And at 36 minutes, I think you're probably done too. So let's go ahead and put a bow on this episode. I really, really want to thank you guys for listening. As I've mentioned before, we're a fledgling podcast, and we really appreciate you listening in. We would really like you to follow us on Twitter, where we are at Poisoncast, which is great. And also, you can go to our website, thepoisoncast.com. And you can follow us there, and maybe give us some new suggestions for topics. We're happy to listen to that and maybe incorporate them into the show. So thanks again, guys, and we will see you next time.